Dynamics of rotational motion of body. So let's consider we have a body, and this body rotates about this rotational axis, which is denoted O, and every axis in 3D space we can define by means of unit vector. Unit vector is denoted by O0 vector. So O0 is unit vector of rotational axis. Omega is a vector of angular velocity of rotational motion. Alpha is angular acceleration of rotational motion. And for our purpose, we need to cut out the elementary mass of the body. The weight of this mass is dm. And this elementary mass is displaced from origin of coordinate system about r, displacement vector. So displacement vector is pointing to elementary mass. C is center of mass of this body. Generally, it doesn't lie on the rotational axis, and RC is a position vector of center of mass. So in a local coordinate system, it's a constant vector, because center of mass of body with respect to body shape or body space, it doesn't change position. Velocity of general point or particle of the body dm is omega by r, and this velocity, tangent velocity, is denoted as it is here. Velocity of center of mass then is vc equal omega by rc. Momentum of rotating body is p, and it is integral of v dm, so we sum the momentums of every individual particle of the body with different velocity over the mass m. So v, in correspondence to this, is omega by r, and omega is constant for all volume of the body. So we can put it out of the integration sign, and what remains is here r dm, and this is well known term because it means a static moment of mass, and we use it for calculation of center of mass position. So we can substitute it, so there is equal rc by m is equal to this integral, so we can substitute it, this integration, by this term here, and omega by rc is, as it was stated here, velocity of center of mass. So momentum of rotating body p is given by velocity of center of mass by mass. Let's talk about law of change of momentum. So change of momentum with respect to time is dp over dt, and in accordance to second Newton's law, it is equal to external force. External force can be considered as all forces, we mean resulting force composed from action forces or reaction forces altogether. Then dp over dt is d over dt of this multiplication, and when we consider that mass is not changing during motion, we consider it as a constant, so we get that it is mass by dvc over dt, and this is nothing else than acceleration of center of mass. So it is m by ac, acceleration of center of mass. As we usually know, the acceleration we can write as a sum of tangent part of acceleration and normal part of acceleration. So we can multiplicate these brackets and we get m by ACT plus m by ACN. If we, in fact, it's all, there is a bit more explanation. So VC, as we already said, is omega by RC, the same we used here. And if we make a derivative, dVc over dt, what is here? So it is d, we make a derivative of this multiplication. So we make a derivative of first term, it is d omega over dt by RC, plus we keep the first term here and we make a derivative of second term, it is drc over dt. And this is nothing else but angular acceleration, alpha, and multiplied by RC, it is tangent acceleration of center of mass, what's here. And this term, drc over dt, is velocity of center of mass, and omega by vc is normal acceleration of center of mass, what is here. So now we can continue when we look at normal acceleration, as it was or said, omega cn is omega by vc, and we can consider that vc again is omega by rc. So this is multiple multiplication of vectors. So we multiply 3 vectors, and for solution of this multiple multiplication we have some pattern derived by mathematicians. So there is triple or double vector multiplication. We have vectors a, b, c, what corresponds with omega, omega, and c, and it is ACB minus ABC. So we can use this pattern for calculation of this. So there is A by C, so it is omega by RC by dot product, by B, B is omega, and again minus, there is A by B, so it is A by B, it is omega by omega, it's here, by finally C, C is RC, it's here, and we continue here, because we can substitute that vector of angular velocity omega is scalar value of velocity by vector properties of axis, because omega has all the same vector properties as O0 vector, as the unit vector of rotational axis, because it has the same direction but it differs only by size. So we can write it like here, that it is omega by this vector, and we can substitute it here. So we can calculate that it is omega square when we continue here, okay? It is omega square, we have 2 omegas here, by O by RC, okay, by O again, minus omega square RC, it's here. Please compare this with this using this. And if we continue, we can put out the brackets omega square is here, and what remains is here. And this is normal acceleration of center of mass, as it was at the beginning. So now we are going to draw this vectors. So when we consider the axis of rotation and origin of coordinate system, and there is a C center of mass, so there is displacement vector of center of mass, RC. Yeah. So when we start from here, O0 by RC, it's a dot product. Dot product of this vector, we can shift this vector to this in our mind and multiply it by this vector. So the meaning of dot multiplication, dot product multiplication, is that we project one vector to the direction of second vector. So we project RC to the direction of axis. So there is perpendicular line, and we draw this projection of RC into the axis direction, and we get this size, not a vector just now, but only size. And if we multiply this size again by O0, we get a vector. We give vector properties to this size. So this is a size of this line, and we make a vector from this line by drawing this arrow. It means by multiplying by O0 again. So we have this vector. So we draw this term. If we subtract it from RC again, so we make a subtraction of this vector and this vector, it is usually made like this. If we subtract two vectors, 1 minus second, we can draw minus second vector and make addition. So I draw here minus RC, and I make now addition this plus this, and I get this vector, this green vector, and this is this vector, this green vector. It's A, okay, it is A, and this is this vector. And if we multiply it by scalar value of omega square, we can get greater or smaller vector. In this case, I have chosen a greater one. Okay, so I multiplicate A by omega square, and this is ACN. So we have a vector of normal acceleration. The tangent acceleration is perpendicular to this vector. Okay, so I draw it in this way, in this direction. If we consider that D'Alembert force is calculated by multiplication of acceleration of center of mass and mass, so we can express it also like this. If we decompose acceleration into normal and tangent components, we get this, and then this represents normal D'Alembert force, and this represents tangent D'Alembert force. So normal D'Alembert force is minus ACN by M, and tangent D'Alembert force is minus ACT by M. So I can draw it in the same direction but in opposite way, because there is minus in both cases. Okay, so in negative direction to this ACN, I draw O force in red color, and in negative direction of this tangent acceleration, I draw tangent component of D'Alembert force. Maybe in two-dimensional view it is more convenient for understanding. So if we look at this picture in this direction against this axis, we see the situation like this, all these vectors. So there is ACT against this, it is T component of D'Alembert force. There is ACN against this, it is O component of D'Alembert force, and this is addition of both red components, and this is addition of both dashed green components. Okay, so another fact what is good to point out is that axis O, vector RC, and vector O lie in one plane. So in this lecture we derived a D'Alembert force either in total or in components of rotating body.